All right, let's work through. This is the Chapter 1 Limits Test Review, Worksheet 2. Again, we're starting off with a piecewise function. And based off of these problems, we want to try to determine the piecewise function to choose looking at the conditions that match the problem. So for part A, we're trying to determine what the limit is as x approaches negative infinity for g of x. So if we're approaching negative infinity, we have to look at the conditions to see which of the piecewise functions to choose. So negative infinity, this matches the condition where x is less than 2. So we're going to be using the x plus 5 over 2x minus 4. Now, when we're evaluating limit as x approaches negative infinity, we think of it in terms of the way that we would looking at horizontal asymptotes, which means if we find the limit as x approaches negative infinity, we can look at the degrees and go from there. So in this case, the degrees match between numerator and denominator. So if the degrees match, then we simply take the ratio of the leading coefficients. So 1 over 2, 1/2. Okay. It doesn't matter if it's approaching negative infinity or positive infinity. If the degrees match, we simply take the ratio. The negative and positive infinity is not going to affect the sign for our limit. Okay, part B. Limit as x approaches 2 from the left side of 2. So from the left side of 2, we look at our condition here, and that matches the first one here. So from the left side of 2, so the first thing we do is we plug 2 into the expression. So if we write this out here, okay, first thing we do is we plug in our target x value. So if we plug in 2, we get 2 plus 5, which is 7. Plug in 2 into the denominator, we get 4 minus 4, which is 0. 7 over 0. Now, normally that would be undefined. However, this is a one-sided limit, so that tells us that we have to go a little bit further. We can't say undefined. We have to provide more information as to why the limit is undefined. And what's happening here is that we're approaching a vertical asymptote. Okay, 2 is causing the denominator to be 0 and the numerator to be a non-zero. So non-zero over 0 tells us that there is a break in the graph and there's a vertical asymptote. So we want to determine, is the vertical asymptote, is the branch approaching negative infinity or positive infinity as it approaches 2 from the left side of 2. So the way we can do that is to decide algebraically, we choose a value that is in the direction of 2 from the left side of 2. So in this case, we can choose 1.9. So if we plug in 1.9, all we need to do is we need to determine whether we get positive or negative for our expression, because we know it's approaching a vertical asymptote. So if a graph is approaching a vertical asymptote, there's only two options. It's either going to shoot up to positive infinity or go down to negative infinity. So if we plug in 1.9, 1.9 plus 5 is a positive value. 1.9 into the denominator. 1.9 times 2 is going to be a value slightly less than 4. So a value less than 4 minus 4 is going to be negative. So then we get a positive over a negative, and that must mean that the graph is approaching negative infinity. Okay, part C, limit as x approaches 2 from the right side of 2. From the right side of 2, we look at our conditions here, and the conditions that match our problem here is 2 from the right side of 2 will be 2x minus 5. So we simply evaluate the limit as x approaches 2 from the right side of 2. First thing we always do is we just plug in the expression regardless of whether we see a plus or minus for the one-side limit. Plug in 2 in for x. 2 times 2 is 4. 4 minus 5 is negative 1. Negative 1 is a real number, so that's our answer. That's our one-sided limit. There's no need to do any further evaluation if we get a real number. Okay, part D, limit as x approaches 2. So in order for a limit to exist, one-sided limits from either side of 2 must agree at the same y value. So we actually have found that from part B and C. So part B, approaching 2 from the left side of 2 is going to negative infinity. From the right side of 2 is approaching negative 1. These do not arrive at the same y value, so therefore the limit does not exist. Part E, if we're approaching 5 from the left side of 5, we look at our condition here. From the left side of 5, we'll be using this condition between x between 2 and 5, so we use 2x minus 5. So if we want to evaluate the one-sided limit as x approaches 5, from the left side of 5 for 2x minus 5, plug in 5 in for x. 2 times 5 is 10. 10 minus 5 is 5. That's a real number. No need to do any further evaluation. Regardless of whether we see a one-sided limit there or not, our answer is 5. Okay. Approaching 5 from the right side of 5. So from the right side of 5, we're looking at the last condition here. So approaching 5 from the right side of 5 for our expression, first thing we always do is plug in our target x value. 5 goes in for x, and we get negative 25 plus 4, which is negative 21. Plug 5 in for x. 5 minus 5 is 0. Negative 21 over 0. Normally, this would be limit does not exist. However, we looked at this is a one-sided limit. So, and we know that the 5 in the denominator will cause this to go to 0, meaning that there's a vertical asymptote. If there's a vertical asymptote, then we're down to two choices, either two options. Either the graph is going down to negative infinity or positive infinity, very much like what we did for part B here. So we can choose a representative x value that is in the direction of 5 from the right side of 5. So in this case, I can choose 5.1 or 5.01. And then I just want to see if this expression will give me positive or negative to help me decide between my two options, positive or negative infinity. So if I plug 5.1 or 5.01, negative, let's see, 5.1 squared will give me a value that is greater than 4. So, so we know that's a negative value. If I plug in 5.1 into the denominator, 5 minus 5.1, 5.1 is slightly larger than 5, so this will give me a negative in the denominator. So negative over negative is positive, so therefore positive infinity. Part G, in order for a limit to exist as x approaches 5, the one-sided limits have to agree. So from the left side of 5, it's approaching 5. From the right side of 5, the graph is approaching positive infinity. These do not agree. These do not arrive at the same y value, so therefore limit does not exist. Okay, approaching 3 from the right side of 3. So from the right side of 3, we look at our condition that matches the 2x minus 5, x between 2 and 5. So we just simply evaluate the limit as x approaches 3 from the right side of 3 for 2x minus 5. First thing we always do is we just plug in the x value regardless of whether we see a one-sided limit there or not. Here we get 3 times 2 is 6. 6 minus 5 is 1. 1 is a real number. No need to further evaluate. That's our answer. Okay, limit as x approaches positive infinity. So positive infinity, we look at our condition here. X is greater than 5. That's positive infinity. That's in the direction of positive infinity. So we evaluate the limit as x approaches infinity for our expression. Now infinity, we treat this like we would horizontal asymptote, and we compare degrees between numerator and denominator. Here the numerator is has a higher degree, so we know that this expression will shoot up to either positive or negative infinity. So we just have to decide which sign to choose. So we can just choose, plug in a representative large x value. So if I plug in, let's say 100 squared, negative plus 4 will still give me a negative. 5 minus 100 will still give me a negative. So negative over negative will give me positive. So therefore, we know the graph is shooting up to positive infinity. All right, use continuity conditions to justify whether our function is continuous or discontinuous. Remember, our three conditions are: does the point exist, does the limit exist, and then does the point exist where the limit exists. So we see that for this piecewise function, we have two branches, one that's to the right of 3 and the other that's to the left of 3. So we're going to just go through our conditions here. We know the point in question is at x equals 3 because 3 is going to be the only potential x value where there could be a break in the graph, because anywhere else, polynomial, exponential function, these graphs will be continuous everywhere. The only place where it might not be continuous or there might be a break is where these two branches are trying to meet up. They may not end up arriving at the same y value. So let's step through our conditions. First, does the point exist? So the point is 3. We look at our condition, x is greater than or equal to 3. So f of 3 will be for the first piecewise function. So plug 3 into the expression. We get 2 times 3 squared plus 5 is 23. That's our ordered pair. Second, we want to test the limit. Limit as x approaches 3 from the left side of 3. That's for 2 to the x. So testing one side limit is a further evaluation of the second condition. So in order to determine if the limit exists, we're going to see if we're going to test the limit as x approaches 3 from the left side of 3, and then the limit as x approaches 3 from the right side of 3, and see if they agree. So from the left side of 3, we just plug in 3 into x. 2 cubed is 8. From the right side of 3, that is for the first piecewise. So if we plug 3 in for x, we get 2 times 3 squared plus 5 is 23. 23 does not equal to 8. We know that on either side of 3, the graph is not going to connect. So therefore, a limit does not exist. And if the limit doesn't exist, the second condition fails. If the second condition fails, we know that the type of discontinuity we have will be a non-removable discontinuity. Okay, number 3, find the horizontal asymptotes. These are special types of problems where if we have a square root in the denominator, we may have 2 separate horizontal asymptotes. We have to test limit as x approaches infinity and limit as x approaches negative infinity. A lot of times what may happen with these types of graphs is we may have something that looks like this, where on one side, as we approach positive infinity, the graph is approaching one y value. As we approach negative infinity, the graph is approaching a different y value. So we need to test the limit as x approaches infinity and also test limit as x approaches negative infinity. So if we're approaching positive infinity, we can just evaluate the expression as is. So in this case, we see the degrees are actually going to match because x squared inside the square root is the same thing as just x. So if we just take the ratio of the leading coefficients, -2 over root 6 will be our limit. Okay. If we're approaching negative infinity, we have to do a slight adjustment. We basically evaluate the same expression. We just have to include a negative outside the square root of our expression. So in this case, negative infinity, we still compare degrees. The degrees are the same. The x squared inside the square root matches the x outside the square root. They're both degree 1. So we take the leading coefficients, 2 over root 6, but there's negative outside. So -2 over negative root 6, so 2 over root 6. We have 2 separate horizontal asymptotes. So y equals 2 over root 6 and -2 over root 6. All right, these are special types of problems where we have to deal with the conjugate of the numerator. But first, we always plug in our x value. So if I plug in 3 in for x, I get 4 plus 1 is 2. 3 plus 1 is 4. Root 4 is 2. 2 minus 2 is 0. 3 minus 3 is 0. 0 over 0 is indeterminate form. We know we can do a little bit further work with this. So we multiply by the conjugate of the numerator. The conjugate of the numerator is root x plus 1 plus 2. We match the numerator and denominator. We're basically multiplying by 1. And then I can just factor or expand this expression out. So I'm going to expand my numerator. And the root x plus 1 times root x plus 1 gives me just x plus 1. The middle terms and outside terms will cancel out. And then the last terms, -2 times 2 is -4. X plus 1 minus 4 is x minus 3. X minus 3 will match one of the factors in the denominator, we're able to cancel those out. We're left with 1 over square root of x plus 1 plus 2. Now we can reevaluate the limit, plug 3 in for the remaining x. 3 plus 1 is 4, root 4 is 2, 2 plus 2 is 4, so we get 1/4. Okay, last one here. Which of the following is true given our piecewise function? This is slightly different than the piecewise function that we see here. Here we have 2 separate branches on either side of 3. Here, the 2 branches are self-contained inside the first piecewise function. The only thing that there's a hole in the graph, and that hole in the graph may or may not be filled in by this ordered pair here. So what we can do is we can find the limit of this expression and see if the limit matches that of this ordered pair. Okay, if it matches, then we know the function is continuous. If it doesn't match, we know that there's a hole that exists outside where this ordered pair is. There will be a break in the graph if that's the case. So let's evaluate the limit as x approaches 3 for the first piecewise function, because we know that the graph will, the limit will exist since this graph is connected on either side of 3. Okay, so if we want to evaluate this limit, if I plug in 3 in for x, I'm going to get 0 over 0. So that tells us we can keep going with this expression. I can factor the numerator using difference of squares. That once I get x minus 3, x plus 3, the x minus 3 will match between numerator and denominator. I can cancel those out. I'm left with this x plus 3. Reevaluate the limit. 3 plus 3 is 6. 6 is the ordered pair where the limit exists. That also is where the point is. So we know that this point is going to fill in this hole. So we know the function is continuous and the limit exists. It fulfills all 3 conditions of the continuity condition. Okay, so we look at our choices here. Limit does not exist. We know that's false because we see the limit does exist. Function is continuous, matches all 3 conditions. The line x equals 3 is a vertical asymptote. Okay, it's not quite a vertical asymptote. We see that there's actually a hole in the graph. Vertical asymptote would be where if we see this x minus 3, if this doesn't cancel out or match up with the numerator, then we can say that there's a vertical asymptote. But here, if the denominator factor cancels out, that will be a hole in the graph.